There are 8 million YouTube talks online, but if you want to really experience it, you have to come in person. It's great. I mean, you'll just meet such cool people.
I'm Dmitry, work for Hudson River Trading, and today we're going to talk about our experience of using coroutines in our production code. So we've been using coroutines for quite some time, a little less than 3 years now. So once compilers, which offered decent coroutine support, made it to our build system, we sought to use them to streamline some of our internal applications, which were massively I/O-bound, and therefore suffered from all possible problems you might imagine in sufficiently complicated callback-based asynchronous code. When we started working on it, we realized some challenges we're going to have to overcome. So first of all, as you might expect from a company with a few decades of history, we have accumulated quite a bit of existing code. Pretty much everything was asynchronous, and which was asynchronous was callback-based. So to gain any chance of adoption, the solution we were going to implement needed to offer a clear story of interoperation with such code in both directions. The next thing is our low-level event loop and I/O multiplexer is built in-house. The first version was merged roughly, I believe, a decade before ASIO was a thing. And once it's then fine-tailored for a few specific use cases and needs, and adopting any coroutine implementation that comes with its own I/O engine, like ASIO, again, was not feasible. And another thing is our engineers often have somewhat skeptical attitude towards fancy new stuff. So to convince them to even consider trying these shiny new features, you have to demonstrate some real benefit of switching. So speaking of benefits, I hope I don't have to sell coroutines to you folks in this room and talk too much about how using coroutines can lead to code that's easier to read, easier to write, easier to maintain, and that using callbacks or equivalently features leads to having to establish and maintain explicit context for your asynchronous operations and manually propagate across stages, which is non-trivial, opens up for certain lifetime management issues, and that any errors have to be propagated and handled by hand without any options of using language features designed specifically for this purpose, like C++ exceptions. So using coroutines may simplify certain things, but that does not necessarily mean that they will. So to get real benefit from the coroutines, we need some cooperation from the implementation, the framework, and the structure of the program, which is going to bring us to the next section. We're going to talk about what structured concurrency really is and why it matters. So if we look at pretty much any asynchronous framework, chances are it's going to be built around the same concept. There's going to be a class which represents a unit of background work. It may be an OS thread, maybe a green thread or fiber, it may be a stackless coroutine or anything else, whose lifetime is often tied to the lifetime of such background work. Then there's a join primitive that will suspend the current task until another one completes, and then returns its result or propagates an exception may have raised. And finally, there's often, not always, but often, a detach primitive, which would dissociate the task from the object that represents it, and would run alongside the rest of the program and simply disappear upon completion. So these detached tasks turn out to be by far the easiest way to mess with object lifetimes and plant some dangling references, as there's simply no way to figure out when a piece of data passed to a detached task is still in use. So this code snippet is simple enough to be obviously wrong, as we passed a local buffer by reference to a detached coroutine, and the buffer is going to be destroyed long before the coroutine might even have a chance to start executing. So fixing this in practice would mean wrapping in relevant context in shared pointers, which would mean lots of shared pointers floating around. But I also have another problem here. If an exception is raised in the detached task, the implementation doesn't have any path of its propagation. So in fact, it is stuck between dropping on the floor or terminating the whole process. This naturally translates to a requirement that any detached task must be enclosed in a try-catch block. But even then, it is often unclear what to do with a caught exception, well, short of logging and discarding it, which is a distressingly common error handling strategy in an asynchronous world. So with these efforts on the context management, error handling, the overall ergonomics of detached coroutines are not that different from good old callbacks. If you want better reasoning and better handling of those problems, the first solution which quickly comes to mind is, OK, remove detach entirely and require every task to be joined at some point. In practice, it would likely mean joining a task destructor, because this is the only function which is guaranteed to get called eventually at some point in time. This kind of resembles the path from setThread to JThread, but even if this is a clear improvement with respect to object lifetime problems, and dangling references problems, error propagation, which might involve re-raising any errors in the calling context, still is problematic. Well, the first thing is destructors are not supposed to throw. But if you have a rule this for your particular destructor, contrary to popular belief, throwing from a destructor is not undefined behavior. It's clearly defined, clearly specified which happened there. But if you have a rule this for your particular destructor, get some guardrails to drop an exception if there's another one in flight, which is also considered bad practice. The more interesting problem is still there. What if actually task destructor is never reached in your program? And this is far more common scenario in asynchronous application you might probably think. Consider this code snippet, which is meant to accept and serve TCP connections, and also tell the supervisor, hey, I'm still alive, don't kill me, don't restart me once every second, which is expressed in the background task here. Ignore for the moment the fact that it cannot handle multiple connections concurrently, and think what would happen if report liveness raised an exception. Such an exception would have been erased when we join the task, but such join follows an infinite loop, once they could have as well put sudden reachable in there. So this was result in practice in a piece of a program suddenly stopping working without any diagnostics whatsoever. So it looks like removing detach was a step in the right direction, but it turns out to be utterly insufficient. The real root cause of the problem is this piece of code executes in background, and then if anything bad happens to it, it's going to sit there idly until some other piece of code bothers to inquire about its fate. That's assuming it is ever going to happen. So to address this problem, we're going to have to eliminate the very concept of background execution, and instead establish one ground rule. A task can only run if, when, and as long as it is being awaited by another task. This awaiting task serves in a capacity of regular caller in our good old structured programming approach. First of all, it's going to resume execution once await completes. But more important property is a corollary. Is once the caller resumes, it can be sure the call is done for good, and any resources it may have used can be freed. And second, this call wait statement is a perfectly natural place to erase any exceptions unhandled by the callee. So these two properties naturally hold in a traditional structured programming paradigm, and with this ground rule and the supporting machinery, we're going to bring them to the concurrent world, hence the term structured concurrency. There's an excellent article by Nathan Smith, Note on Structured Concurrency or Ghost Statement Considered Harmful, which I highly recommend reading, unless you have already done so, which is going to justify all these ideas in much more detail than I'm going to here. Okay. So now equipped with these ideas, let's try to sketch an API that accounts for what we just discussed. As we just noticed, if we have a task type which represents async function invocation, so merely having it as scope should not kick it off. It's awaiting the task should start it. So this naive code snippet would not work as its author may be expected. In a sense, there won't be any concurrent execution here. First, task 1 starts and runs to completion. Then so does task 2, giving total execution time of 2 seconds. So storing a task in local variables is therefore absolutely pointless and generally discouraged. The natural question that may arise at this point is how you run multiple things concurrently. For this is the whole point of having a asynchronous framework. So here where we start adding combiners, functions which group multiple awaitables together in one. So the first awaitable which quickly comes to mind is this all of, which would start all its arguments in parallel, then wait until they all complete, and then collect and return the results as a tuple. If any awaitable raises an exception, it would cancel anything still running, wait until cancellation completes, and then re-raise the exception to calling context. We're going to cover cancellation a bit later. Once we have all of, the next thing that comes to mind is any of. Like all of, it would also start all its children in parallel, but as soon as any one of them completes, it would request the cancellation of the other, and once anything still running gets canceled, it will return a variant of return type with children awaitables. So any of turns out to be remarkably useful for a variety of scenarios. If you need to put an upper bound on runtime execution of some task. The most trivial use case is attaching timeout. Let us suppose you have a long-running function which does some sort of a networking I/O, therefore can run arbitrarily long and hang forever. So the traditional way of making sure your program won't hang with it is for the function to accept explicit timeout and then propagate it further downstream along with some careful accounting calculations. There's another nice article on why this approach is either tedious or leads to breaking abstractions, or maybe both. But if we have this any of, then we can use it to combine a long-running thing with a trivial awaitable, which is simply resume its parent after a specified amount of time. And this pretty much solves the problem. Instead of putting a delay, we can put an externally triggerable event object and publish a reference to session event somewhere to make the operation cancelable from the outside. So anyone having access to this event can call its trigger function to abort the operation early. Another use case is implementation of a clean shutdown of daemon process upon receipt of signal. Like normally, what you could routinely see is for the main serving class is the need to listen for signals itself and interacting with IO event loop, which is not that good practice. But again, once we have this NEO, we can combine it with a awaitable which would resume its parent when the signal is received, and then use NEO to cancel it. And of course, NEO can be used to implement racing. So here we have a resolve on function which performs a DNS resolution against a specified DNS server. And if we need a resilient DNS resolution, we first kick off a resolution on Google DNS, and if it doesn't reply within 100 milliseconds, we kick off backup resolution, this time in Cloudflare, and return whichever results come first. So if we draw all the awaitables we've seen so far, tasks, combiners, sleeps, input, output, etc., as a graph showing which awaitables await which, we find out these awaitables naturally form a tree, very similar to a regular call stack you've seen before, but branching on all of and any of combiners. So every node in the tree has another node suspended and waiting for its completion, which gives us a natural path for propagating exceptions. Likewise, cancellation naturally propagates down the tree. So once we need to cancel a node, what we'll have to do is recursively cancel all its children and then confirm the cancellation to the parent. So good. It looks like properties we wanted to achieve naturally hold so far. Let's now give our API a shot and write kind of a hello world of concurrent programming. A simple concurrent TCP echo server. To quickly come up with the idea of splitting it into parts, serve function, which would take an established connection, read bytes and echo them back, and listen, which would accept incoming connection and spawn serve as needed. So serve is relatively boring and uninteresting. We have a buffer, an infinite loop, we synchronously read whatever data is available, write them back. And we're using Boost.Asio for this example, which reports any errors through exceptions, we catch them and return. Listen is going to be a little bit more interesting. We're also going to have an infinite loop when we accept an incoming connection, and what we're going to do with them next. We need to somehow run serve concurrently with the next iterations of our loop here, but so far we haven't seen any means of doing so. So, well, one option would be to take the statement literally and rewrite the loop in a recursive way. But, well, both ergonomics and performance would be questionable at best. But this will work, well, for some definition of working, and might point us to the right direction. Because if we draw the task tree of this solution, we'll see this long list of listen invocation interleaved with any of. So the tree actually degenerates into a linked list, holding multiple serve invocations and never cleaning them up. Wouldn't it be nice if instead of all this nonsense, we had just one sort of a dynamic all of, holding accept and any number of serves, adopting as more come in, and disposing of them as complete. This would be really nice, but the question here is, how can we express such a thing in C++ code? So the first thing that comes to mind is something like this. Okay, we have an object of a class whose internal structure is yet to figure out. And use the method start provides to spawn more tasks. But this is going to violate our ground rule, because once we call start, it should actually kick off the awaitable, but there's anything waiting for its execution and suspended. So this task spawned to this dynamic all of doesn't have a clear, available error escalation path. So what we should do instead here is to resemble this sketch we've drawn more closely and have listen suspended on our dynamic all of and handle the first task, but also equip this first task with a handle it can use to add more tasks there. So now if we draw the resulting task tree again, we can find out that it almost perfectly matches normal C++ nature rules. We have a listen, which is suspended on our dynamic all of, which is suspended on the lambda, which is suspended on async accept. This approach gives us an interesting thing. a node in our test tree which is bound to a variable reference and task's argument to lambda in this case. So what we can do now is start adding functions there. It can be helpful. We already have start or add. We might add size, might even get cancel. So with the arrival of the latter, it figures out our dynamic of a little outgrown its purpose, original name. So it's not just simple Olaf. So what we have just created is the fundamental primitive of structured concurrency. It appears pretty much in any framework which has word structured concurrency anywhere near its description, and always under a different name. Python Trio, which more or less pioneered the approach, calls them nurseries. A recent addition to Python async.io has similar working task groups. There is task scope in Rust, there is coroutine scope in Kotlin, but the whole idea is the same. To give a way to spawn a task which runs concurrently with the spawner, but make sure they all exit before leaving the scope. For the lack of universally agreed upon name, and because our HRT engineer is more familiar with Trio than with anything else, we also call them nursery. And mnemonic, a place where children are. So one drawback of this is it works pretty well, but opening a nursery block requires quite a lot of typing. But with some creative abuse of operator overloading in C++ macros, we can reduce the syntax down to this. So now both ergonomics and performance are acceptable, while the structured and concurrency invariants still hold. So one important property of a nursery, probably one of the most important property, is that it lacks a public constructor. So it can only be created through this macro, and since the macro features a co-await, it can only be created in an asynchronous context. So the nursery also has a parent task, and with it, it has a clear error propagation path. And for the sake of completeness, let's write our main function to see how it might look like. Because at this point, you might have a question. If you only can run a coroutine if it's awaited by another coroutine, how to kick off the first one? So to address this, we have a top-level run function which accepts an event loop and an awaitable, not necessarily coroutine, but most likely so, and kick it off, and then run event loop until the awaitable completes. Obviously, it returns the result of the awaitable, or rethrow any exception may have raised. And we can also apply the previously discussed technique of clean shutdown of signals, with signal set awaitable to cancel listening coroutine upon receipt of a signal, and also cancel any server coroutines which it may have spawned, and cleanly shut down sockets. So this concludes our echo server exercise. Nurseries and combiners share some common properties. They all act as node in our test tree. They always wait until all the children complete before resuming the parent. If any child raises an exception, the exception will get re-raised in a caller context, but not before any children still running get canceled and confirm their cancellation. So all in all, we never let anything run unsupervised. Not even when it's cleaning up. So okay, we put quite some effort into making sure that any task spawn will complete before the spawner does. But one might ask, but what if I do need to spawn a task which would continue running after the spawner exits? Alternatively, what if you need to spawn a task from a context which is not a coroutine context? Well, you cannot break the rules. Those are there for a reason, but you can bend them to a degree. If you open a nursery, then you can pass a reference to the nursery to the third parties, and they can use the reference to spawn tasks there. So a listen may have been written, totally pointless, but totally acceptable and perfectly legal, as this. Note that now begin listen is a regular function which accepts a nursery explicitly. So while this allows us to circumvent the rules, it still happens in a controlled way. So first thing, every task still has a caller, in a sense that the caller is the thing that we're going to return control to, in this case, a coroutine which opened the nursery block. It is going to deal with any unheld exceptions the spawn task may raise. And of course, this does open up a possibility for dangling references, as any local variable possible reference into this task is going to get destroyed when the spawner exits. But passing around nurseries looks like advanced enough to attract extra scrutiny from both reviewers and the authors, make sure there's no dangling references involved. The task spawned still cannot run uncontrolled, because their lifetime is still bound by the lifetime of the nursery they have been spawned into, unlike detached task. And last thing, the function behavior with respect to whether it spawns any tasks can be trivially deduced by the functional C++ signature. A regular function cannot spawn any tasks because it lacks any means of doing so. An asynchronous function can spawn tasks, but is required to join them before it returns. So whether it spawn tasks or not can be considered as an insignificant implementation detail, and a function, either regulars or asynchronous, which takes a nursery, well, chances are it's going to use it to spawn tasks which might outlive it. So what passing nurseries around free function is, from our experience, and an extremely rare use technique, I don't remember any single occurrence of this in our code base, it is much more common within a class. So let us suppose we're building a sort of a process manager for whatever reason. I know, is this dissatisfied with systemd or not? First, we have our run process function, which does everything we need to run a process. Prepare the environment of the process, wait for its completion, capture, log its output, maybe restart upon failures, so on and so forth. Then we have our start function, which needs to start the process in the background and then return so the process can continue, can actually start executing. As we just discussed, the easiest way to do this is to have a reference to a nursery and use this nursery to spawn the tasks there. But this raises the next question: where to take the nursery reference from? We already mentioned that nursery can only be opened in an asynchronous context. And C++ lacks asynchronous constructors, even more importantly, asynchronous destructors. So the most obvious approach would be, if a class requires the nursery to function, take it in the class constructor. This, however, brings certain problems with crisscross object lifetime. Consider this code snippet we're putting our supervisor to use. We open the nursery, then we construct the supervisor around it, then we work with it somehow, and leave the scope. At this point, supervisor is already destroyed, but any task spawned into the nursery will continue running. And if any of those were a member function referencing a nursery object, then the reference to that object which went out of scope. So the better approach would be for a class to open nursery itself. Have it expose a run function, which would open the nursery, then stash the reference to the nursery in the class variable, and then suspend forever. Working with such an object would require first creating it in scope, and then using any of to combine its run function with an asynchronous lambda which interacts with it. Well, a little toilsome, but that's probably the best we can achieve until C++ gets asynchronous RAI, assuming it's ever going to happen. There's been a proposal in standard 1662, but its face remains kind of blurry at this point. So yeah, that's what we're going to use. So far, we've been talking about spawning and combining. First, about how would you introduce a primitive asynchronous operation like sleep for, we already mentioned. So if you've been to any talks on C++ coroutines or read any introduction to the topic within the last, 4 years, you must have seen this triad of function which is an awaitable must define. So first, we got await suspend, which should initiate the operation, accepts a pointer size and trivially copyable coroutine handle, and should arrange its resume method to get called whenever the operation completes. Then we got await resume, which is called after the parent resumes and should return the result of the operation or erase an exception. Or we got await ready, which is a performance optimization, allowing the runtime to bypass await suspend entirely and go straight to await resume is awaitable, managed to already complete by the time we were going to suspend on it. So this is the composition: start the operation, notify when it completes, and then hand back the result. Turns out to be quite versatile in practice, and allows expressing pretty much any asynchronous operation except in a completion callback as a C++ multi awaitable. For example, let's consider this interface provided by C-Average library for performing asynchronous DNS resolution. Here we have the initiation function, as getAddressInfo, which accepts a name to be resolved, some other uninteresting stuff, and the completion callback along with a opaque pointer to be passed to the callback with the result of the operation. If we want to wrap it into a C++ awaitable, the first thing we need to do is to provide some space for storing the arguments for initiation function in the result. And then our await suspend would save the coroutine handle, then call the initiation function, as getAddressInfo, pass it the argument, pass it this for a opaque pointer and the callback, which would copy the result of the asynchronous DNS resolution back to the object and then resume the awaiter. And which resumes pretty straightforward. So this approach is universally applicable. The general idea is that any operation which accepts a continuation callback can be rewritten as an awaitable, whose callback would resume the awaiter. Okay. Now let's talk about cancellation. So this is one of the most important features in any practically useful asynchronous framework. We already said that our branching nodes, all of, any of, nurseries, can cancel their children in certain circumstances, and now let's talk about what this means in practice. As you might have guessed from advertised use case of any of, cancellation is an extremely common and widely used operation in the asynchronous world, but in order to be practically useful, it needs to have certain properties. First of all, it should be built-in and implicit. Just like C++ exception eliminate the need to accompany every function call with this if failed, return failed, a good concurrency framework should likewise eliminate the need to write if cancel return anywhere. Next thing should be fast, which means in practice should not be implemented through C++ exceptions. Exceptions are widely used to implement cancellation in a number of frameworks we've seen, but the overhead of throwing and catching a C++ exception is way beyond what we're comfortable with. And perhaps most importantly, cancellation must be asynchronous in a way that cancellation may be requested and then completed later, and the framework must be able to deal with that. The asynchronous nature of cancellation is often overlooked, and I'd like to further emphasize its importance. So some asynchronous operations are immediately cancelable. At any point, you can tell them, please cease to exist from now on, and will comply. Some could have been made cancelable, but the API lacks any means of expressing cancellation. If you try to provide a awaitable wrapper against a synchronous C API, chances are high it's simply going to look like this, but there's no sort of a handle inside we could use to communicate cancellation requests to the library you're trying to wrap. And some operations inherently cannot be made synchronously cancelable. One of the most trivial example is running subprocess. Well, you could try to kill it, but you still need to wait until the kernel processes your signal and delivers to the process that flushes output buffers, which may take some considerable time if network mounts were involved. And only then the process exits and the exact status is communicated to the parent. If you were to wrap and running subprocess into a C++ awaitable, you need to account for that. And you cannot afford to leave the dying process behind. Imagine you have this code snippet which runs the process in a shooted environment. Well, you prepare the environment, then you do a number of bind mounts to bring dev, proc, and sys there, and then you run the process. If you cancel it, the process needs to be fully exit before you can proceed with the unmounts, because those mounts may be still being used by the process. And if you leave your running process behind, you cannot clean up your environment properly and reliably. You're going to have to cascading chain of failure in the cleanup of your thing. Another textbook example is asynchronous I/O, like I/O you bring in Linux or overlap I/O in Windows. I'll talk about the latter as it's easier to fit in one slide. Here you have your read file X, which takes an overlap structure, which is going to serve as a unique point of the operation, unique identifier for the operation, and the completion callback. If you use cancel IOX to request cancellation of the operation, you still have to wait until the kernel processes it and later calls your callback and deliver notification of happened cancellation. Before that, the overlap structure and the buffer is still in use by the kernel, and if you free it prematurely, well, you have a textbook use after free error, with the exceptions not going to be called by any sort of address sanitizer or whatever. Well, you can, of course, choose to disregard all this, but then you're opting out from ever supporting asynchronously cancelable operation. And if it turns out you do need them later, well, you're going to have to backport asynchronous cancellation in an already existing framework, which is going to be, well, entertaining. Rust folks learned this the hard way. Originally only supported asynchronously cancelable operations that hit them quite hard. So, okay, now we've talked about the properties of usable cancellation, so let's go ahead and implement it. The procedure structure in structured concurrency world would be the same for any other awaitable. Take the cancellation request, proxy it further down to your children awaitables, wait until they carry out the cancellation, confirm the cancellation on your own, and proceed with object destruction. For task, the last bullet point is solvable. C++ offers us coroutine handle colon destroy function, which could be called on a suspended coroutine to destroy the promised object and any parameters and local variables still in scope. But the first two need cooperation from the awaitable. We should be able to tell it we want to cancel an in-flight operation it represents and provide it a way to notify us when the cancellation is carried out. We're therefore going to extend C++20 awaitable interface with a new function, await cancel, and model it similarly to await suspend. When an awaitable carries out the cancellation, should resume the coroutine handle we passed to it. And we promise to only pass the same coroutine handle we previously passed to await suspend, so a trivial implementation which doesn't do anything and instead allows the operation to complete naturally is totally legit and valid implementation. But now that we have defined an awaitable interface we're going to invoke upon cancellation request, we need to figure out how to call it. To be able to do that, we need to keep track of the awaitable object on which the coroutine is currently suspended and its type to call the correct await cancel function. But the language is not going to provide us any assistance with it. So in order to solve this, we might take advantage of the promises await transform method. As a refresher, when coroutine co-awaits on an object, the object first is passed through promises await transform if it's defined, and the other await underscore methods are called on the result of such a transformation. So here's how we can sketch a promise object, which we may use it to keep track of its child awaitables. Well, first, we need a pointer to the object in its await cancel. Now put our await transform, which simply wraps the awaitable into a class interceptor, which we're going to implement. Then its await suspend delegates to the wrapped awaitee, but not before it saves the pointer to the object and its await cancel function, so we can call it in the future. Await resume simply delegates to the wrapped awaitee, so it does await ready. So with all this tracking in place, all we have to do is utilize it when implement cancel function of our promise object. Another problem arises from a need to actually carry out the cancellation and go ahead and destroy the coroutine. Coroutine handle : destroy can only be called on a suspended coroutine. And once our awaitee resumed us, we're no longer suspended and cannot call this destroy function anymore. It's undefined behavior. So we need a way for the awaitable to notify the promise about the completion of the separation, but without actually putting the coroutine back on the CPU. But we have chosen to pass type-erased coroutine handles to the awaitables, so they can resume coroutines without any knowledge about promise types that backs it. So there's not much of anything an awaitable can do to a type-erased coroutine handle, besides of simply resuming it. It would be nice if we could pass it a coroutine handle it could resume without any knowledge, but such resumption would instead invoke a function of our choosing instead of just outright putting the coroutine back on CPU. Turns out this is in fact possible, but to accommodate for that, we need to dig deeper into some implementation details. As you likely remember, when a coroutine function is invoked, it runtime allocates a frame on a heap whose structure depends on the function being called, and whose contains resume index, which is basically an index co-wait expression is going to resume at, the promise object, all arguments the functions, all local variables in scope, all temporaries whose lifetime spans across suspension points, and other compiler-specific bookkeeping. Of course, the layout of such a frame is not standardized, not going to be standardized, it's compiler-specific. But compiler vendors took some effort to make sure coroutines compile, but different compilers can interact with each other. And in order to do that, all major compiler vendors agreed on the first two members of a coroutine frame. Those are pointers to resume function and destroy function specific for the coroutine. So coroutine handle resume can therefore be written like this. Simply take an address stored in handle, cast it to a frame header, and then call its resume function. So equipped with this knowledge, we can put up a fake coroutine handle and stuff whatever function we want in its resume fn. Now we can amend our promise object, equipping it with a fake coroutine handle in addition to a real one, and have it provide two handles. The real one, whose resumption would indeed put the coroutine on the CPU, and the proxy handle, whose resumption would simply invoke promises on resume function we were going to implement. In order to do that, we only need to install the trivial trampoline in our fake coroutine frame, like this. And now the only thing left to be done is actually modify our interceptor class to pass in the proxy handle to the awaitable's await suspend method. So now when the awaitable completes, we're going to end up in our onResume, but the coroutine is still technically suspended and totally eligible to be destroyed. So we can go ahead and destroy it if we want to. So this completes our coroutine cancellation procedure. So looking on awaitable interface again, one must notice that certain functions naturally make up pairs with one function, in each pair reversing the effect of the other. So what does it mean in practice? For example, framework will not call await cancel on an awaitable whose await suspend has never been called. So ideally, especially if the awaitable is not immediately cancelable, it should be await suspend which initiates the operation, and the object should lie dormant until suspended on. Again, merely having an awaitable in scope should not kick off the operation. If that's not feasible, and it's not in certain circumstances, you'll need to account for a variety of edge cases like operation completing before being suspended on, or maybe even awaitable being immediately destroyed without ever suspending it. And also keep in mind that eagerly started awaitables run unsupervised until co-awaited on, which does not play nice with structured concurrency invariants. So yeah, beware. So the next non-trivial thing to cover is how to manage lifetime of objects and ensure proper resource cleanup in an asynchronous world. Well, RAI has been there for over 40 years now, but now it is even more important than it was before. Consider this obviously wrong code snippet. Resource cleanup in Happy Path likely immediately and rightfully caught your attention, as you know that if anything bad happens, if anything before it raises an exception, close will not be called, and you're going to have a textbook resource leak. However, you could have gotten away by wrapping the thing in try-catch block and duplicating the cleanup code in the catch clause, and then raise the exception. Despite looking ugly and violating DRY, that might have worked until now, as any function in try block could either return normally or raise an exception, and we seem to have accounted for either case. However, the cancellation opens up for a third possibility. The whole coroutine might get canceled in the middle. As there's no exceptions are involved, we're going to skip close on both branches and have a resource leak back. The right way to employ would be to employ destructors to do the resource cleanup. In this example, you could use a scope guard offered by multiple extensions to standard library, which call the close upon its destruction. And as destruction of a coroutine involves destruction of all its local variables, close will be reliably called regardless of how exactly coroutine ceases to execute. Of course, it would be even better to just use standard file stream, whose destructor would just close the file without having to deal with scope guards and whatnot. Things start getting a little bit more interesting as the function performing cleanup is itself asynchronous. Suppose we have this interface, which might in fact make sense if we deal with network mounts, where opening or closing might involve network round trip, and we want to work with it. Well, we already talked about drawbacks of having cleanup of a happy path, but an attempt to employ RAI here doesn't work either, as destructors cannot be asynchronous, and therefore no co-await expression is allowed in a scope guard body. So to help with this case, we have added another awaitable combiner until cancelled end. We should take an awaitable and then sit there idly. Its await suspend will not kick off the awaitable, and it's going to sit there idly until cancelled, and then it will kick it off and wait until its completion. And only after its argument completes, it's going to confirm the cancellation. So if combined with any O like shown here, then in either case, whether Lambda executes normally or raises an exception, or the whole thing gets cancelled from the outside, anyway, the second argument to any of is going to get cancelled eventually, therefore triggering the asynchronous cleanup. So we consider this pair, until cancelled end, paired with any of, to a degree an asynchronous equivalent of RAI, which we're going to use until C++ has a clear story of RAI in coroutine context again. OK, now as we discussed in the beginning of the talk, if you start introducing coroutines to an existing code base, chances are it's going to the asynchronous AO scenarios are already handled in it somehow, and most likely through the callbacks. So if you need to fit in these scenarios, quite likely that our piece will sit somewhere in the middle, being called up from upper levels and calling things to lower levels. And both these layers can be asynchronous and callback based. So we'll need a way to interact with them. So one direction is calling callback based functions from coroutine context. So here we have begin thing, which accepts a continuation callback, which will be invoked when the function completes. Well, we'll already have discussed how to bridge such function to a coroutine. Simply wrap it into an awaitable, like we did to see Aries early in the talk. It's going to cost us about a dozen lines of code, which is kind of tolerable. The other direction is a little bit more interesting. Suppose we are required to implement this interface and this function, which would fill in the passed-in buffer and then invoke the passed-in callback. And we have an implementation expressed as a coroutine, which we are going to use. Again, we already talked about how to approach such a thing. Establish yourself a nursery, and then submit a coroutine, which would delegate the read and then call the callback. And of course, we need to account for all possible errors, so try block is really non-optional here. The non-trivial function here, the non-trivial question here is where to get this nursery object from. Early in this talk, we had discussed implementing a run function, which should open the nursery that can be later used by the class, but it was required the class to only be usable from asynchronous context. If we can afford this, to have a chain of coroutines all the way up to the top-level run function and processes main, then good, we solve our problems, nice. But what if we don't control what's up the stack? What if we are implementing a sort of a plugin, a shared library, which will be called into some process which doesn't know anything about asynchronous framework and all these task classes we're going to use? To account for this case, we added an unsafe nursery. It behaves like a regular nursery, but it does has a public constructor, so it can be placed in a class just like a regular function, just a regular member variable. should be well understood that unsafe nurseries exist for the sole purpose of violating structured concurrency principles. It's kind of ironic how we put so much effort into making sure these will hold, and now we're providing a way to circumvent them on purpose. But that's life here. All tasks submitted to unsafe nurseries will still have a parent node, which is going to be the unsafe nursery itself, but the unsafe nursery doesn't have any parent, instead acting as a separate root node of a totally isolated task tree. Practically speaking, that means one consequence of this is that unsafe nursery doesn't have any way of error propagation. So if any task submitted to the nursery raises an unhandled exception, we're back at slide 1, not having much of any other options between choosing between dropping it on the floor or terminating the whole process. The other problem is, since unsafe nurseries have a public destructor, such a destructor can be called at any moment, and nursery needs to make sure there won't be any running coroutines left behind after its destructor returns. But we already talked about how asynchronous things are not necessarily immediately cancelable. So what we can do is we can make one attempt to cancel anything still in flight, and if anything transitively submitted to the nursery happens to be immediately cancelable, then good, we can proceed with the destruction. Otherwise, again, we're stuck choosing between leaving running things behind or terminating the whole process. Practically speaking, however, it doesn't bring too much additional pain because unsafe nurseries exist normally mostly for the purpose of bridging different modules implementing different paradigms, callbacks versus coroutines, and things like asynchronous destruction or error propagation need to be addressed anyway. So even if the nursery didn't terminate on an unhandled exception, you still have to catch them and communicate them to your caller somehow, through errorback or through calling the callback differently or some other problem-specific way. So you'd still have to have this try-catch block in here. It's really non-optional, regardless of how the safe nursery behaves in such a case. Likewise, you cannot destroy an unsafe nursery with still have running tasks in it, but most likely your unsafe nursery is a member variable of your problem domain specific class, and tearing down such a class which still has in-flight operations is still a logic error, so asynchronous teardowns still need to be accounted for somehow in a problem domain specific way. So in conclusion, a few words about our own experience. We have implemented an asynchronous framework around the ideas I talked about here. It has been available internally for almost 3 years now. We have employed it in a number of our IO-bound applications. So whenever we take a piece of code and re-implement it using coroutines, we routinely see about 40 to 50% code size reduction. I mean source code size reduction, not talking about binary size. The control flow becomes much easier to read, understand, and modify if necessary. We also value our uniform interface to asynchronous cancellation and timeouts. Those used to be so difficult to implement using callbacks and state machines, so cancellation was overlooked much more frequently than we're comfortable with. As one example, in one fuse file system implementation worked on recently, I was able to implement request interruption by kernel, so how network connections not result in uninterruptible sleeps, have been written about like 15 lines of code, which is kind of a decent result, if you ask me. On the other hand, the ideas around which the framework is built certainly require some getting used to, and certain things need to be learned, taught, and communicated. And of course, there is an effect on performance. Coroutine optimization is still, in the mainstream compiler, is still premature at best. Plus, the framework adds some amount of its own overhead to carry out all this cancellation tracking and whatnot. But all in all, after almost 3 years of using coroutines in our IO-bound application with complex control flow, we can see that they are indeed helpful. They do simplify certain use cases. So we decided to share it with the community a few months ago and release it on GitHub under MIT license, and hopefully it will be as useful for others as it has been for ourselves this whole time. So that's all I have for you today, folks, and thanks for coming. And if you got any questions, we still have 15 minutes left. Thank you.
Thank you. That's a great talk. Have you been following the P2300 work in the standards committee, and have you been thinking about working with it with your library?
Yeah. Question on P2300. So the thing predates P23 because, like, again, it started shortly after coroutines were the thing. So right now we don't offer any sort of like interaction procedure with this. Again, we probably, if we started to implement this today, we probably have chosen, like, I know, to adopt like senders as a universally agreed upon like interface for asynchronous operations. Instead, we modeled on a slightly enhanced C++ 20 awaitable interface. But again, we do have certain like concerns about practical usability of senders receivers in its current form and its current shape. There's certain things like our equivalent of nurseries or async scopes, or when any, I believe, had not been standardized. They exist in some implementations, don't exist in some other implementations. So I guess if sender receivers get some widespread like use by the community, we're going to put some like bridging in there, or probably like reconsider some other like things and provide interaction with this. So right now we don't provide any, but yeah, probably gonna reconsider sometime in the future.
I'm the co-author of the paper P3149, which is proposing async scopes. So if you don't get any other questions, I'd love to hear your concerns about where that's going and what you're thinking.
The main concern with async scope I have is its existence in public constructor and public destructor. So again, you've probably seen this, how we talk about like this async scope can only be handled, can only be opened in the asynchronous context. And then when the thing completes, we need to everything respond into async scope executes and completes until we resume the parent. And with existence of public destructor, we open up for a possibility that the thing didn't tore down at any point in time. I believe there's let with async scope thing, which has been added recently, which is definitely a step in the right direction, probably more closely resembles what we come up with our like what we call nurseries. But still, again, I remember, I think counting nursery, which is equivalent of our unsafe nursery, is still there. Unsafe nursery is still there. And if we're going to pursue further there, I would probably appreciate some sufficiently big warning signs that this thing has these drawbacks and these pitfalls, and you got to be aware of them when you use them. But it's kind of like glad to see that that P2300 authors, after like 2 years of talking about structured concurrency, actually bringing themselves closer to what structured concurrency really is, which is ditching the idea of detached execution once and for all.
Since I still have the mic, does your unsafe nursery have something analogous to the proposed join method on the async scope?
We do. So yeah, we can actually have a variety of ways to turn an unsafe nursery into a regular. So there's an awaitable join. We should do the same thing to turn this into a regular nursery. It will establish a clear error propagation thing. So now any errors thrown by task spawn to this nursery will not lead to process termination, will get erased there. And also we have, because we mostly target unsafe nursery use cases as a bridging with legacy callback style paradigms, we also add this, what we call async close thing, which would cancel anything in there and then evoke a callback over it passed when the nursery is truly empty, it can be torn down.
Thank you.
Thanks for the talk. The question I have is around how the nursery works. So I do like the idea that for a task to run, you need something to be awaiting it, to basically, be responsible for joining it and also handling any errors from it. With regards to the example you had where you have the TCP server and you create a nursery and you spawn a new task for every listen that succeeds and you perform something on the socket, you have the await on the entire nursery to basically make sure that that's waiting for all those tasks. However, in that example, I'm guessing the behavior there is if one of those tasks, let's say, it throws an exception, returns an error, everything is sort of cancelled, and then the awaiter, the caller, is immediately notified like, oh, here's the error, one of your children failed. I'm guessing that's like a sort of toy example for the presentation, but in a production server, ideally, if one of your socket handling code throws an exception or error, you still want the other ones to run, but also handle the error for that one separately. So is there some way in the nursery to, like, I suppose, I guess, get like a stream of errors as they occur while still allowing like these existing tasks to run?
Well, the thing you want last about this is letting errors drop on the floor. So we still, yes, upon receiving any errors, yes, we cancel the whole thing, and then we raise the error from begin nursery of an open nursery block. So if you need any other error handling strategy, you're absolutely free to implement this by enclosing whatever you spawn there in a try-catch block. which is normally be used for any like production-ready code. But yeah, again, if you accidentally forget to do this, when we absolutely don't want to, if we don't want to leave you any possibility of dropping exception on the floor without realizing it. So any opt-in idea when you would like have a stream of things, a stream of errors, when you can choose not to consume errors from is really not an option.
Thanks.
Hi. You mentioned the performance overhead. Could you elaborate a little bit? Are we talking about 1-2%?
On performance overhead, there's been some numbers. So yeah, as mentioned, it's probably 2 years ago, so probably at least they could be a little bit outdated. But I put some reference number in there. So you can see like switching from one coroutine to another is an equivalent of 1 malloc, and we have heavily optimized malloc G, I believe, if I remember correctly. And spawning a coroutine, so an overhead of calling asynchronous function is about 3 mallocs. And you can see this is all negligibly small compared to any syscalls. So performance advice I've been giving to our engineers within HRT is as follows. When you think whether to employ this thing, employ like asynchrony, employ awaitables and coroutines for modeling your operations, ask yourself how long the operation would normally take. If it's a few nanoseconds, probably it's not the best choice for you, at least for now. If it's around 100 nanoseconds, less than one syscall, then you'd probably still model it as you would do now, using a state machine of sorts. But instead of accepting a completion callback, you would code upon when the thing completes. You take a coroutine handle, which you would resume. That would still have tolerable performance overhead. And if you feature at least one syscall, if you reach out to kernel for whatever reason, you don't have to worry about it. The additional overhead for coroutines wouldn't be noticeable by anything.
Thank you.
Okay, any other questions? Well, I guess since nobody has anything else to ask, then thanks for coming, folks, and enjoy the rest of the conference.